the following video I will explain how I adapted the idea of a NMF, a non-linear matrix factorization, to refine a polyphonic piano tracker. So what I'm after is to only place a microphone or two microphones into the piano, no extra MIDI devices or piano bars or anything. So we will only work with the audio signal from the piano and deduct the polyphonic pitches played in real time as fast and as reliable as possible. Obviously, this is a task which is impossible because the piano has the first couple of milliseconds, the first 10 to 20 milliseconds is the hammer noise. We have a hard time distinguishing between the different pitches because the hammer noise is not equal across all 88 keys, but it is too similar to know exactly what's going on at the very beginning of the sound. So then we can look into the sound a little bit later, but obviously with that we accrue some delay in order to be on time. So there is a delay involved and we have to work around that, and there is certainly no precision as working with a MIDI keyboard. But for what I'm after compositionally, I found a good middle ground to detect the pitches for what I want to do. The idea behind the NMF is to build a polyphonic model where each key would be one channel in the NMF. And then in real time with NMF match, we will compare the incoming signal against the database of those analyzed pitches and then find the matching ones. As during this past year I had no access to a good grand piano and my upright piano at home is totally out of tune, so I was relying on the physical model program Pianotech to train my model. And while thinking about concert practice, it is obvious that instruments in different concert halls are of different types with different tunings. Not only the diapason, so not only if it's at 440, 42, etc., but also their internal tunings. So well-tempered is not necessarily well-tempered from one tuner to the next one. So in order to take all of this into account, I made a quite massive loop here where I'm looping through all pitches and I choose 4 different piano presets. So the first one would be an equal temperate Steinway. The second one is a well-temperate Steinway. The third one is a Bechstein in equal temperate, and the last one is an upright piano. So the upright piano also I put it into the condition kind of a little worn out, so it's not as pristine as the other instruments. So by presenting for each pitch during the training cycle different instruments, different tuning systems, so different bass tuning pitches, 3 dynamics between piano, mezzo forte and forte, and then with and without pedal, I made a database of a little over 6,000 sounds presented to the training model. And so if I would initiate this, let's say right now I'm presenting 2 pianos, let's take just 1 tuning system, 3 dynamics and without pedal, and I start my loop, then we will hear the different pitches being played. So you hear the difference of the 2 different instruments, the different dynamics. As you can see, I'm actually omitting the lowest octave of the piano. I'm not analyzing them. That is due to their frequency range. We would need a much higher FFT size in order to analyze those pitches correctly. And the higher our FFT size, the longer is the delay during our resynthesis or the analysis and resynthesis. So I'm omitting the last octave. I'm working with an FFT size of 4096, and that has worked pretty well across the entire range of the piano. So I'm starting at this C, which in the American standard is C2, and going up to the highest pitch of the piano. So with this little messy patch, I was able to combine and test all kinds of different combos of, okay, so how is it if I'm only analyzing one pristine piano in one pitch, I mean in one tuning pitch, without pedal, etc., etc. So I was training for a couple of weeks different models, and that led finally to a model I started liking and which seemed to work pretty well. In this patch I will now explain a little bit more in detail how the piano tracker works and compare the input signal against the output signal. The patch itself has on the left side one instance of the piano tech, that's this one, and I'm using a MIDI keyboard to play this model. The output of that sound goes into my piano tracker, and for now I also will feed it into the left channel of our video. And then the red portion here is the right instance of the piano tech, and this model will receive the analyzed MIDI pitches and play them back. So by comparing the original sound on the left channel and the analyzed sound on the right channel, you can observe the time latency we are getting between the two, and also all the mistakes the analysis makes. So let's start from the top, where obviously the analysis is of higher quality because our FFT is more precise. And then the more we go into the lower range of the piano, the more you will observe that it is not so accurate anymore. When I'm starting to play more than one pitch, you can also observe that this will work better in the higher range. So in that octave it works very well. So up to 3 pitches it's pretty reliable in this range. If I'm going down, then it's much less reliable. Because now we are getting all these other overtones of the lower pitches also triggering higher pitches. But I don't mind, this will be part of the piece. The piece is called Sparks, and the idea of a contact point between two high energy entities creating a spark, creating something which explodes from there out. So I'm taking this as a model to generate musical content from the original piano notes, which then spark off sounds which are close to it, which are in that range and which are based on that harmony. The analyzed data from the training patch I explained earlier in this video ended up in a 73 channel sound file. So that is kind of our database where we have the NMF fingerprint for each key in a multi-channel sound file. And this one gets now loaded into our piano dictionary buffer. Let's now have a look into the analysis of the NMF and how that works. So our piano signal comes in here. I'm filtering the low ends. I'm only letting pass the high frequencies above 200 Hertz. I'm using the NMF match object with 73 components with the same FFT settings as during the analysis, iterations 10. And if you observe what comes out of the NMF match, here we see actually the list of the 73 activations, and when a sound comes in, then we see whatever those values are. So the first operation I'm doing is I'm taking the mean value of that entire list, and I'm comparing every single activation component, whether that is 5 times above the mean. If so, then I let pass the information. If not, then I'm setting that particular component to 0. The funnel is adding to my activations the MIDI node numbers. I'm using the Barsiv object here to filter then from all those 73 nodes only those which are above a certain value. So right now it's 10. So if I turn this gate on and I play a note, turn it off and inspect that list, then right now only one single band was above that value. Okay, yeah, we see that's the note. And if I play something like a chord, then we see, okay, here is a number of MIDI values with their respective activations. So I'm sending these activations now into 7-3 parallel instances of a note filter, if you like. So let's take the one for MIDI note 60. Inside each filter, each pitch filter, I'm looking at successive analyses. So with the current FFT settings, NMF match gives me roughly a new analysis every 10 milliseconds. And I'm grouping always 2 together, and I'm looking at their relative difference. I want that the value of the activation is actually increasing, and when it's decreasing, I'm kind of ignoring it. So only if there's an increase in 2 successive activation analyses for this particular pitch, then I'm using this activation value with some scaling to transfer it into a MIDI velocity. And I'm also having a note thresh off. So while these values come in and for this particular note the activation falls below a certain threshold, then I'm triggering a note off. All these parameters can be set individually. I noticed that the absolute values of the activations are pretty much dependent on the FFT size and the overlap, etc. So I keep those parameters kind of as variables here. I can then set to depending on the analysis I'm using. So that's pretty much it. So after this, you see I'm actually not using an segmenter. So I experimented a lot with all the slicer objects we have, looking into spectral segmentation or into temporal segmentation. After all of this, it worked best for me on the piano with this huge range of dynamics to just rely on the activations information. What you see here is a little trick that if the overall energy coming in from the microphone drops below a certain threshold, then I'm sending a note off to all my MIDI notes. So that is just kind of a security to be sure that after all notes have been lifted, that there's no lingering MIDI note kind of continuing. One family of prepared sound files for the work, for the electronics portion, also comes from the Piano Tech virtual physical model. When we play it, we have access to many different parameters, how the soundboard reacts with the strings, etc. A normal note would be just like this. So that is a pristine piano, but then there is this randomize function which applies certain random values to all kinds of parameters of the physical model, and every time we press this button we are obtaining a slightly different or radically different type of sound. With the different max patch, I created a database of sounds where I'm triggering the different pitches, and every time for the next pitch I'm generating a new random and render them into 3 different dynamic values. So In total I have now 15 different sounds for each key on the piano keyboard. And in this patch I have now in the database 1152 sounds. I'm loading them into the sampler object by Serge Le Mouton, and depending on the velocity I'm obtaining now different sounds. In this portion of the video I want to talk about my attempts to classify sounds. I made with Piano Tech these random sounds, so they're all on one single pitch here, and we have 16 sounds in fortissimo, 16 mezzo forte, 16 in piano, but because of their randomization they don't necessarily always represent piano sounds or mezzo forte sounds. I was searching for ways to order them from the most present sounds to the least present ones. Let's first listen to some of those sounds. So these are the A flat 5 random sounds. I just play a few examples. So as you can clearly hear, they vary in presence, in pitch, in qualities of resonance, etc. So if I try to take the 30 nearest neighbors here, and let's say I'm starting with this sound here, I will explain how I'm getting to this 2D representation in a minute, but let's just compare the two results first. So I'm clicking on this one, and that will start my search for nearest neighbors with this particular sound. But as you can clearly hear, there are moments where two successive sounds don't seem to be in a series of progression towards more brilliant or progression to a different quality. And that has to do with the concept of nearest neighbor in a 2D space. So if this is my starting sound, as you clearly heard, we went into this area, but at some point, this particular point here becomes the next nearest neighbor. And that is particularly true if you search for long chains of sounds, and then it has to jump to this one, which suddenly makes a huge difference. So let's play them back slightly quicker, starting again with this one. So you hear all these jumps, and from there on I thought, okay, so perhaps this concept of nearest neighbor comparing to my starting sound is perceptually not what I need. What I would compare while listening one sound to the next is actually the last one's nearest neighbor. So I want actually to start with this one, and then if I'm getting here, probably this is the nearest neighbor, and then probably this is the nearest neighbor, etc. Now let's listen to this approach with a chain, starting again with the same sound here. This is much more in the direction where I would say, okay, yeah, each successive sound is somehow related to the one preceding it. So let's play a few examples. I'm playing back a little faster and start at different points here. What I like about this approach that it doesn't just go linearly from a brighter sound to a softer sound, but it explores different zones, sonic clusters in my 2D representation. Let's now have a look into the details of this patch. So first I'm taking a folder, in this case it's my A flat 5, and I'm making a 4D male band analysis. So in here I'm taking each sound in a loop, and then I'm making a 4D male band. From there I'm getting the stats, and the stats are then selected, so I'm only taking the mean value. So after this, the stats are a buffer, the mean or a buffer. So I see here with this little patch that I have 40 channels with one single value. And then from the mean, I'm flattening it into a new buffer I call MLP point. And that is now a one channel buffer with 40 values. So these 40 values are now put with the add point into a dataset MLP point. And let's print into my Max window here. If you look at this and print it, that's our dataset where we have for each of the 48 sounds my 40 columns with the 40 male band values. I now normalize them, so now I have a second data set which is called MLP data normalized. And now I will use the autoencoder. So obviously all of this is based on modifying the help patches. So I'm taking the 40 neurons as my inputs. I have 3 hidden layers, one with 9, then going down to 2, then again 9, and then my output layers are 40 again. So I'm using the autoencoder to reduce the information to a 2-dimensional space. This will take a moment, so we should repeatedly fit our input data, which is the data normalized, into, again, the same data set, data normalized. And with that, the autoencoder will learn what coefficients to use to represent in 2 dimensions almost the same output data as the input data. So I have a little machine here which looks at if this fitting parameter is already below 0.1. If not, then do another round. As I guess this network is randomized in the beginning, sometimes it can get into a long learning process, and I have just a second mechanism here. If I already made 40 steps, 40 full cycles of learning, and the value has not decreased, I'm reinitializing everything and start anew. So let's start this. Most of the time it takes about 20 cycles. Sometimes it's faster, sometimes it's slower. It just depends on the sounds and on the randomization of the autoencoder in the beginning. After training the autoencoder, we will now predict the data, or we create another data set which is MLP data reduced. And that one represents our 2-dimensional hidden layer in the middle of the autoencoder. After creating that data set, I now tell the autoencoder to take that hidden layer as my input. Here we can see the print of our 2 columns, and again we will scale that in order to make it now a range of 0.1 to 0.9. That is actually just a way to use this LCD in a more convenient way so that our points don't end up here exactly at the edge of it. So our visual space here is represented between 0.1 and 0.9 on both axes. After that is done, I can now fit my KD tree, and I'm asking for 30 neighbors here. I will now calculate the 30 nearest neighbors for each of the points in my dataset. If I click here, it will go through all of them, calculate the nearest neighbor for each of them, and then I will collect them. As the nearest neighbor always also includes the sound itself, I'm excluding it here, and I'm getting a long list where this is for my first point, those are the nearest neighbors. This is my second point, the nearest neighbors, etc., etc. So let's examine how this chaining process works. Let's start with point number 1. Its nearest neighbor is probably this one, the index 4. So let's investigate how that process works internally. So let's say we start with point number 1 and we look into this list here. We see, okay, the nearest neighbor of my first sound is number 4. So then we jump to number 4 and we see the nearest neighbor of 4 is 15. This is number 1, this is number 4. So the next one is probably this one, yes, 15. Then we go to 15 and we see, oh, the next one is 14. Very probably this one. What happens if we are at a sound and the next nearest neighbors is the previous again? We would kind of create an endless trill between these two, because this one finds its next nearest neighbor being this one, and then this one refers back to that one. So in order to avoid that, in my chaining process, I'm verifying whether a sound is already in my list. So every time I'm creating my chain, I'm updating this list here. So this list is constantly growing while I do this repetitive looping through all possible points. And only if the proposed next nearest neighbor is not yet in the sounds we have already accumulated, then it is added. If not, we are going to the next nearest neighbor, or if that's needed, to the next nearest neighbor, etc. So that explains that I can't know exactly how many items I'm obtaining at the end here. So I say it's the longest possible chain, and that longest possible chain depends on where I start. So let's say I'm starting here. And now it ends. I don't know if you saw that, it ended around here. Because now all remaining nearest neighbors of that sound had already been played. These remaining elements are actually outside of the scope of the 30 nearest elements of the last dot. And that is actually good. So then I'm actually avoiding a jump to an unrelated sound, which is the next nearest, but sonically not necessarily related to what we just heard. So this process has worked pretty well for me.